Alright, I'm almost done with this board. I'm just going over every single track on the PCB. Even though it's a very tedious task and it does take some time to do that, it's worth it. It's very important. I find so many little details in the tracks that need correction. And usually it's things like something that occurs because I moved another track, and that moved another track, and maybe that moved another track, and then I end up with connections that are suboptimal, or I have like bits of track that are just dangling. Basically, little details like that. So it's very useful to go over each track this way and to correct anything that I find. Let's see. So next on the list here is U24 ENC SH2, and U24 is here. Let's see, got the designator there. Also the designators, for example, some of them need corrections. Some of them would do better, like placed a little bit, maybe moved somewhere else. And sometimes I find also the designators that are maybe overlapping something, maybe have too many vias in the way. Like this is fine. It's like when this is sent to the manufacturer, they'll automatically mask out the via, so there will be a certain part of this designator missing. But in this case, it doesn't really matter because you will still see that it's R136, and if you don't see it, you can always look in the PCB and just search for it. Let's look at this pin SH2. So SH2 is probably somewhere here. There. It's going like that. So looking good there, looking good. Also, I correct things like, for example, if I try to keep the connection as 45, like every single bend in the track, I try to keep it at 45 degrees, if possible. Sometimes it's not practical to do it, but where possible, I try to keep it to that, because it helps signal move through the track, and kind of like if we can fix it, why not fix it? That's the way I look at it. If I see something that could be a problem, it doesn't have to be a problem, but it could be a problem, then why not fix it? Let's see, this one is probably locked. Let's see. Kind of like that. And this goes here, it's totally fine here. We have a little bit of a bend there. Fix that. Okay, this is fine. I select the full track using the I key, and then I can toggle the locking bit, or just click in the properties of the track to lock the track in place. This is very important to lock it in place, because if I don't do that, if I then try to move another track, I'll mess up my previous track that I already reviewed. So I don't want that track to move or be moved by the push and shove router. ENC-Z2, where is that? ENC-Z2. There. This one got a bit weird. It doesn't have to be that way. It's just got that way because that's how it ended up being when I maybe moved something around, or simply because I was just routing it, just trying to get it routed quickly and move on to something else, because it doesn't really make sense to route the tracks exactly like tracks usually need to be moved. Many tracks have to be moved as the design progresses. So putting any effort into kind of doing it properly from the beginning doesn't really make sense, because you still have to go over all of the tracks later and double check that everything is correct. So it's better to put in the time into doing a review in the end and save the time when laying out the circuit board. Let's see. So when I lay out the circuit board, I just care about I just care about keeping the tracks as short as possible, and try to find a balance between keeping them short and keeping the overall topology in a way that makes sense. Sometimes it's not possible to keep the tracks short. For example, sometimes things need to be routed to the connectors. They have to be long. I can't place this chip here because I have my motor switching circuit here, and I can't place this one anywhere else because I have my power here, and this needs to be connected closely to power using thick traces. So yeah, it's things like that. So it kind of like trying to make the layout as like trying to place the tracks. It's kind of like track placement in the beginning, and then during this review, it's the final routing. Let's see, U24C67. It's a bit cumbersome in KiCad to do this because I cannot search for a particular net. I have to search for the component, and then I have to find the actual pad that connects to a particular net. Also here I try to make as many of the tracks as possible go out of the pin along this side, along the short end of the pin, because it's if the track, for example, comes in like this on the side, and this adds copper to this pad, it could affect the solder joint. It doesn't have to, but it could do that, and that's enough of a reason to, as much as possible, make sure that the tracks go out on the short end of the pad. Let's see. So I was looking for this C67. I could search for C67, but this chip is sufficiently small that I kind of try to find the right pad just by looking for it. This one goes here. That's fine. Let's see. I lock it, and P43 pad 2 could be here somewhere. This goes all the way here. We don't need this band, I think. We could sometimes there are all kinds of little glitches in the routing. Come on. There we go. Definitely. About this one. Yeah, probably will have to just let it be. I think it was fine now. P43 pad 2. Yeah. P44 pad 2. P44 pad 2. And like for example here, I could make this come out on, let's see, come out like that. And the reason for doing this, to have a 45-degree angle there, is that if you have sharp corners, I don't know exactly, I can't point to exact application note that describe that, but what tends to happen is that you get higher EMI on the sharp corner, which kind of can be explained by the fact that electrons are essentially like a flow of liquid, and if you have a sharp turn, you will have a wave that kind of goes up vertically, and then the water flows. Kind of, you get a disruption in the flow, and it seems to be the same way for electricity. That if there is a sharp corner, then there is a disruption in the flow. So it's kind of always better to have the corners as smooth as possible, or 45 degrees. That's how it's usually done. But yeah, it's always interesting to find the exact description when talking about some principle, like why do we do this? What is the reason that we route it in this particular way? It's always nice to find some references for it. And I could probably find some references if I search for it, but I'm not going to do that now. I have to finish this PCB right now. Let's see. And there was another thing that came up in the last video. It was related to the routing of the crystals, and I never placed crystals on a different layer from the microcontroller. I think that crystals should be connected. Let's see, no, it's not that one. Crystals should be connected with as short tracks as possible to the microcontroller, and any bias should be avoided. Anything basically that can mess up the integrity of that signal, because crystals are very sensitive, or like crystal oscillators, not the crystals themselves, but crystal oscillators are very sensitive to noise. So anything that increases the noise, no matter how little, is a bad idea, I think. And but of course, it's not enough for me to just say like, okay, this is how I do it, and I do it because of my principles. So I found a few application notes that actually describe it, and it's actually very interesting. There are a few other tips that I didn't know about, and I think it's always like I always accept tips. Like if somebody gives a tip, I always kind of try to evaluate it. Does this make sense? Will this work? And if I learn something that is better than what I've been doing before, then I very easily can change my mind and just do it in a different way, because I think the goal is to do it in the best way possible. So it doesn't make sense to be kind of like to try to say that, oh, we do this, we've always been doing it this way, and that's how we do it. That's how we're always going to do it. That's just bullshit. That's just lame. So I appreciate any tips very much, and I usually accept them, and then I look up the information, and if it makes sense, I use it. If it doesn't make sense, I do something else. So, did I just lose track of my PCB track? Yeah, I think that is okay. Yeah. That's fine. U25. Where is 25? So as always, if possible, make them come out on the short end. And ENC to VDD 5 volts. So that's going to be connected over, let's see, that wire could be a bit bigger. That's a small wire. So it's things like this as well. If there is a wire on the power path and it's too small, this is kind of problems that are getting noticed when doing a detailed review like this. I'll just unhide this layer. So this is the copper layer that goes on the power layer. This is a few copper fills, and all of this kind of constitutes the power connections. Oh, by the way, just noticed this one. That's not good. Let's put a ground layer there as well. I can actually do it like this. So even though it's not strictly necessary to have a ground connection there, I already have, let's see, yeah, I already have ground connections to the ground layer, but it's still a good idea, and in this case it's because keeping the PCB as flat as possible is also a recommendation. Because if a lot of copper is etched, then if I have copper etched here, but not like, if there are gaps in copper, then the PCB kind of becomes, could become, it doesn't, like, modern PCB manufacturing is really nice, so it doesn't matter really, but it's still one of those recommendations that just sort of keep the PCB as flat as possible, and if you have any copper that you remove, like sometimes people will put like ground fill on the top layer just to make it kind of just to make sure that it's the same thickness of the PCB everywhere. Let me just see here. So this one needs to be there. And I don't know how much truth there is to that, if it really matters, but why not? And in this case, it actually makes sense to have an extra ground because this is a high power connection. This goes to the main power connector. So this ground also serves the purpose of leading away any heat that is generated at the connections to this power connector. So kind of like a little bit of an extra heat sink. Anyway, I have this 5-volt power that goes to the to all of the encoder connections here. I'm going to make sure that this fill is properly structured here. So make it a bit bigger. Okay. I'm going to try to find references for any of these recommendations that I bring up. way too easy to accept something as being true, but without having references, without having an explanation, or a set of explanations. It's also very easy to assume something to be necessary or true, and then it doesn't have to be true or necessary. So, I think I need to refill it. I think this will disappear if I refill it. Yeah. Okay, that one's fine. Should I add more bias to it? I think this could be a very, like, this is 900 milliamps. Let's see how thick it should be. So, PCB calculator. 0.9 amps. Yeah, it can be a thin track that just goes and connects all of this together. So we don't need to really think about either making this thicker or putting more bias into it. It doesn't really matter. So, next on the list. Let's see if I can get both windows up. U25, ink or current. Yeah, this one's a bit messed up here, for example. I need to change the grid. I'm going to use a much smaller grid for manipulating tracks, because they're much harder to align properly if the grid is too large. Okay. And I already reviewed that track, so I locked it, but I just saw that there was a chance to make it slightly better, so I did it. And like here, things like this, I tried to avoid things like this, and just move the track so that it connects in a straight manner. Okay, so we got overcurrent 1 and overcurrent 2. These two are fine. Yeah, so I can lock both of them. U26. Actually, I'm just thinking that since we've been talking about crystals, it's probably a good idea to review the crystals. And I'm going to bring up the application notes that I found. These were just first results on Google, but a lot of the advice given there is pretty standard, and there are many other application notes out there. I'm pretty sure there are that pretty much give very similar advice. So I'm going to open up this application note. This is from NXP. This is for a crystal oscillator. Brings up some theory, and then there is the layout. So this is one of them, and then there is another one that comes from Microchip. And this doesn't have to be true. We don't have to accept this as truth. But when different sources give the same information and the same recommendations, it's kind of better to err on the side of applying those guidelines than not doing it. So let's see. We have two crystals here. We have Y1 and Y2. I think we only have two crystals. It's the main microprocessor crystal. Actually, we should have a crystal there. This is Y3. Right, Y3 doesn't appear here because we have here just one of the, like, all the nuts that go to Y3 are probably already defined by the lines that are referring to these capacitors. But we have three crystals. Let's start with the main microprocessor crystal. So, let's see how well all of these guidelines apply to this crystal. It's highly recommended, in order not to risk failure and having an unstable oscillator. Means that we're better off applying these than not. Even though we may not be able to prove that this actually works on this particular board even, but it's just recommendations. So, it's very sensitive to stray capacitance and noise from other signals. It should be placed away from high-frequency devices and traces in order to reduce the capacitive coupling between crystal pins and PCB traces. And this is already a problem for this crystal, because this crystal is it's pretty close to this VSA1, VSB1 and VSC1, and these are pulsating voltage sensing signals. They're not high voltage, they already are conditioned to go directly to the ADC, but nonetheless they're still pulsating currents, which the crystal is not going to like. And also the traces here are different length, so preferably it would actually be nice to rotate this crystal and maybe place it like this, place it a little bit farther away from these traces. I cannot really remap these traces, I think, because all of my ADC channels are in use, basically. There is very little room to rearrange things in terms of connections to the processor. So I will have to try to meet the guidelines by just rearranging this this crystal itself. So let me just disconnect the wires that go here. And this is actually good that there is this reset signal. It has a pull-up resistor, so it's much more stable. It won't be affected by the low voltage oscillations from the crystal, but it is placed between the crystal and these traces here. And what I'm also going to be doing here is probably enclosing this crystal in a ground guard trace that goes all the way around this circuit. Like, to me, this package of this crystal, it just seems odd. It's so I don't know if there is some kind of idea with having a layout of the package done in this way, but it would be nice if I could place these capacitors close together. But yeah, no matter how I rotate this package, it still has a weird layout. It has pins across, and these ones are not connected. So let's place this one there. And there are no traces underneath the crystal, and keep other digital signals, especially clock lines, frequently switching lines, as far away from crystal connections as possible. The ground connection for the load should be short. The ground is basically a ground plane, and on this path, so everything is going to be flowing to the power connector. So the currents will go like this, and we are avoiding the high current, the high current flows from here. But yeah, there could be some disturbances. It's really hard to tell. I don't know if there could be disturbances from this EtherCAT interface, if the signals that return from here to the ground of the power connector would somehow disturb or have the potential to disturb the crystal. But let's just make sure that we keep any digital lines as far away from it as possible. We have this PWM signal as well, which is kind of unfortunate that it had to go there. And maybe, so this is an analog signal. It would actually make sense to place this one on the back, I think. Let's see. Or to place it here. You can place it on the back, and maybe would that be a good idea? Yeah, I'll place this one on the back, and it has to be close to the pin because it's a filtering capacitor. But I could place it essentially here, and I could have a wire then that goes to the analog pin. All right. I'm going to try to keep the rosette a bit far away from the voltage sensing analog lines. And we have to make the traces as thin as possible to avoid any capacitance, and they have to be placed. They have to be placed as far away from each other as possible as well. So we have this trace. It's actually better to lead it out as soon as possible and not have it close to the other one. And this is also part of the recommendations, that the stray capacitance between the traces should be kept to a minimum. Load capacitor should be low leakage and stable across temperatures. The load capacitors should be placed close to each other. I could imagine that maybe placing the load capacitors in the back could be an option, but I'm not going to do that either. I'm going to avoid any vias that go on these connections. Actually, I'm going to also rewire this one. Make it go directly there. Parasitic capacitance will reduce. The gain margin is basically the frequency response of the crystal. I could possibly make a video about that if I would simulate the crystal and try to find the variations in how it performs depending on different inductances on the path between the crystal and the oscillator. But yeah, I'm not gonna do that or even be concerned about that for now. Reduce the parasitic capacity between crystal in and crystal out pins by routing them as far apart as possible. That's done. Ground area should be placed under the crystal oscillator area. This ground land should be connected to the oscillator ground, which in our case it's basically the ground, the layer that defines the ground. Is there any? Yeah, I would guess that the oscillator ground is just connected to the main microcontroller ground. So this should be fine. Crystal housing, we don't have a crystal housing. We don't have at least a metal crystal housing. In case there is only one PCB layer, it is recommended to place a guard ring around the oscillator. Yeah, okay, so that's only when it's if it's one PCB layer. But we could do that anyway. This will help isolate the crystal a little from these signals, and it will give these signals basically a path to ground before reaching the signal and disturbing it. So what I'm going to do is add a ground fill on the top layer here, and just cover this area here. So this will just go around the crystal. We can place some wires here. that should meet all of the design guidelines. And then there is this other one. This describes, let's see, laying out the printed circuit board for the oscillator. This, okay, this is a culprit oscillator sensitive to external components of the PCB. This guidance provides some necessary information about PCB layout. The external component connection is shown on figure 4. Oscillator components on MCU side of the board, no bias, no ground or power planes under oscillator components to minimize parasitics. Yeah, no ground or power planes. We have, let's have the cat out here. So yeah, it would kind of make sense that having a ground plane that also connects then to something here, which results in current flows through the ground plane towards the power connector. But having that could affect the crystal, but it's really hard to tell what the actual effects would be. Let's see. Keep out tracks, keep out copper pores. Okay, cool. Alright, hopefully I haven't messed anything up here. Ground should still be, yeah. Okay. Highly recommended guidelines for crystal circuit design and layout. Failure to meet these guidelines can result in unstable crystal operation or failed crystal startup. I've never had any of these issues, even without using like stuff like this. But since these are the guidelines and they're widely available and we have them, why not just apply them? Parasitic capacitance is probably the most critical of any layout issue. The crystal pin is not as sensitive. Alright, this is for the this is for this particular chip. Do not, right, okay. Do not put ground plane or power plane under the crystal. So maybe we should also remove the ground plane. Which kind of messes things up a little. Let's see. So apparently we shouldn't have any ground plane at all, according to this guide. And when there are such, when there are so many different little details that have to be taken care of, and some of the requirements are a bit conflicting. For example, well, they're not actually conflicting, but since one of the requirements is to isolate this crystal from any of the traces here, and one way to do that could be by placing the ground ring around it, but as the guide has mentioned, they mentioned actually a ground ring and not a ground fill. So it seems to be also important to minimize any capacitance between the crystal traces and the ground. So having a ground fill is not the right choice, which means I'm going to remove this ground fill. Let me just select the ground fill. And if I'm going to have any kind of ground that will shield the crystal from the sides, then it would have to be a ground trace. I'll just leave it like that. And because we don't have ground underneath the crystal now, we should have a ground trace. And this doesn't seem to be in conflict with the guidelines. So if I connect the ground trace around like this, then I could actually connect it to the ground in one point here. And then just have this one go around all the way here. This is a weird layout. Like, I've never done crystal layout in this way. And this recommendation was also only for single, was it single layer board? Let's see. So this kind of actually connects then to the ground that's closest to the oscillator. So probably this can be considered like a crystal ground. Or do they actually mean one of the side of the oscillator that's connected to ground? Okay, now this is taking too long time. I'm gonna leave it this way. Decouple the power supplies of all processors as close to the processor as possible. That's done. Do not cross sensitive signals on any layer. Yeah, and that's done as well. So any of the crossings that we have on this board are separated by the ground plane. So they're as far as possible. One being on the top layer and another one being on the bottom layer, which is another reason to actually structure the layers this way, that you have signals on top and bottom, which brings them farther apart. Okay. And mount all the oscillator components as close as possible. So even though this is for the IMX processor, it still applies for any processor. So place this crystal as close as possible. Right. Let's have a look here. Let's place a cutout on all layers. And all the way around here. Like, I'm very skeptical about doing the ground this way. Very skeptical. I don't know. What do you think? I'm very skeptical about placing a ground, like connecting it like this, then connecting it to the ground plane here somewhere. That just seems wrong. I'll just place the cutout and I'll make sure that the vias connect to the ground plane. It's kind of half common sense, half educated guesses based on application notes. Yeah. How will we actually go about measuring interference here? I suppose we could like measure across this gap here from the crystal, from the pin that goes to the oscillator to the closest ground pin. Like have a probe that connects directly to this pin and directly to this pin, and checking if there are any coupling, any coupled signals on the oscillator. I guess maybe there is a better way. Do you know a better way? Okay. And I'm not gonna do this crap either. I feel like that's just lame. that just feels wrong. Although the cutout is probably a good idea, but doing this routing of the, like having a ground as a trace, I don't know. I feel uncomfortable enough doing that I think I'll just not do it. All right. So this should hopefully at least keep any return currents from this circuit away from the crystal, have them flow around the crystal. And we have another crystal, I think. Where is the other crystal? It's here. The CanFD crystal. First of all, this is going to be 154. Alright. Let's add a keep out. Alright, this should meet the guidelines, at least. That's it for the crystals. I can greenlight all of the nets that are there, and I'll greenlight any other nets when I get to them, if I haven't done so already. So, U26. And I've just noticed that there is not much time left for this video. So just a few more nets and then I'll stop the video. U26 R205. Probably better just search for R. Okay, that's fine. U26 pad 13. This one. Pad 6. This one. That could be like that. It doesn't matter as much for this particular package because the pads are sufficiently large, and I just make sure that it's the right angle to avoid any kind of little little places like that where the general recommendation is that having as few sharp angles as possible keeps the etching fluid from gathering in those places. I don't know how true that is for modern PCB manufacturing. It seems to work just fine. Modern PCBs turn out just fine regardless, but yeah, still good to follow recommendations. It's better to follow recommendations and debug after following recommendations than to debug something that is that doesn't work because you didn't follow recommendations. That could waste a lot of time. U27 R80 pad 2. U27. This is the current sensing. It's a very important track. It has some crossings there and some crossings there, the ground plane in between. Unfortunately, we cannot avoid these crossings. So we'll have to rely on the ground plane. U27, so A, so B. All right. I'm going to lock that one and lock that one. A little bit of extra capacitance there is fine. That one. I think this one is locked. I think I checked this one. No? Probably not. I could lock that one as well. And SOA2. This one. All right. There's just a few nuts left. So I'll finish them off. I don't think there is anything interesting here. It's basically the same process. And then when I'm done with this, I will. Then it's time to actually plot the Gerbers, and then this board is done. All right. Thanks for watching.